Hello students, Professor Dr. Mink. Welcome to another exciting lecture for computer organization. I hope you really enjoyed the numbering systems lecture. I know, you thought this was a programming class. It is. We are going to do some programming. And those topics, floating point, two's complement, binary, hex, ASCII, they are going to be used extensively in the rest of this class, so hang in there. Next, we're going to talk about the A in ISA. ISA stands for Instruction Set Architecture, and this is the microarchitecture piece, which discusses the digital logic structures underneath that support the instruction set. This is not an electronics course, but this is as close as we're going to get to electronics. We'll be walking up to the line of demarcation between computer science and electronics. There's a hybrid field called computer engineering, which kind of blends the two. And we'll be looking at the building blocks of the logic circuits necessary to implement an instruction set. First, we need to discuss transistors. Transistors are the building blocks of computers. They're the smallest component, if you will, of digital circuits. And the original 8086 processor was first developed. It wasn't distributed mainstream, but it was developed in 1978, and it had 29,000 transistors. The Intel Pentium 4, about 20 years later, had 48 million transistors. The Intel Core i7 8086, there it is, the great grandchild of the 8086, which was released 2018, has 3 billion transistors. And we're talking about a difference in speed of megahertz versus gigahertz. I think the original 8086 was, let's see, it was 5 to 10 megahertz, and the current i7 8086 is available in between 4 and 5 gigahertz speed. That is the clock speed of the processor, which we're going to talk about in very significant depth later in this course. So logically, each transistor is a switch, and they are combined to implement logic functions and or a not, which are then combined to build higher level structures, adder, multiplexer, decoder, register, and those are then combined, if you will, in an architecture design to build a processor. And we're going to talk at length about how a transistor and then a logic circuit and ultimately a higher level structure works, but we're not going to build any in this course. But let's get back to transistors. I'm sure all of you have used a simple switched circuit. In your home, where you work, there's a switch on the wall, and when the switch is open, which is typically labeled off, there's no current allowed to flow through the circuit. So if that switch is connected to a light or an outlet with a light plugged in, when the switch is open or off, the light is off. When the switch is closed, which is often labeled on, almost always, there's a short circuit across the switch which allows current to flow and the light turns on. So these switch-based circuits easily represent two states, on and off, open, closed, voltage, no voltage, or in the case of a binary environment, a 1 or a 0. 1 meaning there is current flowing across the switch. 0 means there is no current flowing across the switch. Hey folks, I need you to pause this video and go back to the timeline in Canvas and watch this video, Transistors Explained. This guy did a much better job than I could with this video. It's really good, and it'll help you to understand the chemistry and physics behind basic transistors. It's a really good video. I promise you you'll enjoy it. And then come back here. Okay? So I hope you enjoyed that video. And let's summarize. MOS, metal oxide semiconductor, transistor. There are two types, N and P type. Okay? N is what you would call normal. When the gate has a positive voltage, there's a short circuit between 1 and 2, i.e. the switch is closed. When the gate has no voltage, there's an open circuit between 1 and 2, and the switch is open. So this picture diagram depicts what a 1 and a 0 look like at the transistor, at the single transistor level. And that's a N-type transistor. And a P-type transistor is the inverse. We'll get to that next. So P-type is the inverse or complementary to the N-type. So when the gate has a positive voltage, we have an open circuit between 1 and 2. And when the gate has 0 voltage, we have a short circuit between 1 and 2. So obviously the opposite of the N-type. So logic gates are built from MOS transistors. And we use the switching behavior of these transistors to implement, using combinations of the transistors, to implement logic functions and or a NOT. And you should know that it's not an exact 0 voltage for a 0. Because of some transient voltage, static electricity, etc. 0 is typically 0 to 0.5 volts, which is very low voltage. And a 1 is typically 2.4 to 2.9 volts in the circuitry. It's not an exact 0 or whatever makes up a 1. That's not going to play a big part in the rest of the content of this class, but it is useful information to have. So as mentioned, we're going to use both N-type and P-type MOS transistors to build CMOS circuits. CMOS stands for complementary metal oxide semiconductor circuits. And remember, a P-type pulls the output voltage up when the input is 0, and the N-type pulls the output voltage down when the input is 1. Now we're going to take a look at our first CMOS circuit, which is an inverter, also called a NOT gate. It's used to implement NOT, which is a logical unary function. And so here we would have on the input a 1 or a 0 coming in here. And this is our output. So if you think about it, we have a source. We have a source coming in here. and we have a ground down here. So if we have a 0 on the input gate, the 0 is fed to this p-type, and a 0 on the input of a p-type, which is the inverse of an n-type, closes the circuit. Okay? So we have a 0 here. This circuit will close right here. And you could see it over here much more gracefully drawn. Okay? So electricity will flow and we will get a 1 on the output. Inversely, that 0 is cross-fed to an n-type, which leaves an open circuit here, so nothing flows to ground. And if we do the opposite, if we have a 1, okay, a 1 on a p-type will open this, so no electricity will flow, and a 1 on the n-type, right, will open. So we will get a 0 on the output. So the inverter has a truth table. This is our truth table that looks like this. A 0 in flips to a 1 out, and a 1 in flips to a 0 out. Next up, we have the NOR gate. NOR, which stands for not or the inverse of or, actually requires less circuitry than OR would. You wouldn't think of that, but it does. So the NOR gate is a binary logic function, or it implements a binary logic function. Binary meaning we have 2 inputs and 1 output. Unary, 1 input, 1 output. In this case, the inputs are labeled A and B. So take a close look at the p-types and the n-types. So a NOR gate requires 2 p and 2 n-type transistors at a minimum. You could implement a NOR gate with more circuitry, but why would you? And there, in the lower right-hand corner, you can see the truth table. When A is 0 and B is 0, C is 1. If you think about OR, the truth table for OR is only 0, C, the output is only 0 when A is 0 and B is 0. So if A or B is 1, C is 1. So the truth table for OR for C would run vertically 0, 1, 1, 1. But this is not OR. So it's the inverse, 1, 0, 0, 0. I'd like you to take a close look at this and walk through this circuit one set of inputs at a time, 0, 0, 0, 1, 1, 0, 1, 1, so that you can understand how this implements these 4 transistors wired in this configuration implements NOR. And here we have the OR gate. And if you look, it has where the output for the NOR gate was, it has, instead of C, it has an inverter. And so all it does is invert the output of the NOR gate, and we get the OR, 0, 1, 1, 1, for combinations of A and B. Next up is another binary logic function, NAND. You're probably thinking, this seems backwards. Shouldn't he have presented AND first and then NAND? Well, just like with NOR, it's actually less transistors needed to implement NAND than it is AND. NAND is not AND. And so to implement not AND, we require 2p and 2 n-type transistors wired in the configuration in front of you. And to look at the truth table, Remember, AND, which is the inverse of NAND, only yields a 1 on the output when A and B are both 1. So if this were the AND gate, C would look like 0, 0, 0, 1. But it's not. It's the inverse of AND. So 1, 1, 1, 0. As you might have guessed, an AND gate implements an inverter where the output for the NAND gate was. And it just flips the output of the NAND gate so that we get the AND gate. A and B have to both be 1 for us to get an output of 1 on C. As we start to explore more complex circuits, we're going to use these symbols. Not, or, nor, and NAND. Because the complexity level of detail is going to be too significant for us to actually show down to the transistor level. Once again, I'm going to ask you to pause this video, go to the Canvas timeline, and watch the video on De Morgan's Law. De Morgan's Law is, in essence, the distributive property for logic. And it's pretty straightforward. I would have created a video, but I found this one and it is just perfect. So watch it, takes a couple minutes, and then we'll come back here and we'll implement and discuss De Morgan's Law. So hopefully the discussion on De Morgan's Law helps you to see that with the use of not, we can convert and to or. And we say that with and, or, and not, a system is logically complete. And we can implement any logic statement with those 3 gates. So in this slide, we have an AND gate, but we're inverting A and B prior to the entrance of the gate, and then we're inverting the output. And if you work the truth tables through, you'll see that's the same as A or B. You should also know that and or can have more than 2 inputs. And we can implement with multiple 2-input gates or with the single CMOS circuit. So in the diagram below, the only time we get an output of 1 is if A and B and C are all 1. All their outputs will be 0. So a short mid-lecture summary: metal oxide semiconductor transistors are used as switches to implement logic functions. N-type, when connected to ground, turns on with a 1 to pull down to 0. P-type, connected to plus 2.9 volts, turns on with a 0 to pull up to 1. So to translate that, an N-type, a 0 at the input yields a 0 on the output, 1 on the input yields a 0 on the 1 on the input yields a 1 on the output. For a P-type, the inverse of N-type, a 0 on the input yields a 1 on the output. A 1 on the input yields a 0 on the output. And most logic functions are expressed with and, or, and not. And as far as De Morgan's Law, we can convert and to or to and simply by inverting the inputs and the output. Believe it or not, we're approaching the line of demarcation I usually use as far as content for the first exam. I like to give 4 exams in this course. Obviously, the last one is cumulative, um, so that students don't have a midterm and a final, and they fumble in the midterm, which can happen. I have to tell you, many students take this content for granted and the ability to demonstrate competency in the numbering systems and the logic gates, and they just they get in over their head as far as not studying enough for the first exam. So we're going to finish the content for the first exam with combinational logic circuits. Obviously, I've not taught this course 100% online ever before. This was necessitated because of the pandemic, but we'll do the best that we can as far as building a test that assesses these competencies. So we have 2 types of logic circuits. We have a combinational logic circuit, which means the output depends only on the current input. That is a stateless circuit, which means when the inputs change, the output changes, and it's not dependent at all on the previous state. So when the inputs change, we say we move to a different state, and the outputs will reflect that new state, and it has nothing, it's independent of the previous state. Sequential logic circuits, which I'm going to present as the first topic after exam 1. The output depends on the sequence of inputs, past and present. And sequential logic circuits are the essence of memory. Without sequential logic circuits, we could not store information from one state to the next. So obviously we're going to take a look at some combinational logic circuits first and show how to use, and then later show how to use sequential circuits to store information. I present to you our first combinational logic circuit, the decoder. Uses for a decoder are to convert memory register address to a control line that selects a specific location, or to convert an opcode to one of n control lines. And an opcode is a 4-bit binary operation code in machine language that we'll get to. It's 4 bits of a 16-bit instruction. So n inputs, and in this case we have 2, yields 2 to the n outputs. So for a 2-input decoder, we have 2 squared or 4 outputs. And exactly one output is 1 for each of the 4, in this case 4, possible input patterns. So, and let me just walk you through this. Where you see the dot where 2 lines cross, that means an electrical connection. When there's no dots, there's no connection. So you could think of these as wires connected, soldered, whatever, or not connected, one running in front of the other, but there's no electrical connection. So you could see A and B are cross-fed to 4 AND gates. And the first AND gate on the right, the top right, is an AND gate that has 2 inverters, P-type transistors, on the input. So A and B is inverted before it gets to the AND gate. So let's walk through this. You get a 1 on the output of that AND gate, the top right, if A is 0 and B is 0. Well, how's that possible? So before A and B as 0 and 0 enter the AND gate, they're inverted by that circle, the P-type inverter. So A00 is fed into that first AND gate as 1 and 1. So you get obviously a 1 on the output. So let's continue with AB00. That's cross-fed to the second AND gate, and you could see B is not inverted. So think about this. As soon as you have a 0 on an input of the AND gate, you don't even have to think any further, right? It's going to be 0. So when we have a 1 on the top AND gate, we'll have a 0 on the second AND gate. A is not inverted, so on the third AND gate, so you got to get a 0. And A and B are both directly fed, no inversion, into the fourth AND gate. So for A, B, 0, 0, you're going to get a 1 on the first or top right AND gate and all zeros on the others. So I'll walk you through one other combination. If A is 0 and B is 1, well, that becomes a 1, 0 in the top right AND gate. Whenever you have a 0 on any of the inputs, whether it's a 2, 3, 4, 57 input AND gate, all it takes is 1, 0, and you don't even need to think about the other inputs. If there's 1, 0 on an input of an AND gate, the output has to be 0, because you only get a 1 when every input is 1. So let's take a look at that combination on the second AND gate. So you have 0 and 1. A is cross-fed into the top. The 0 is inverted, so you've got 1, and B is fed directly in. So you've got 1 and 1, so you're going to get a 1 on that second output. So you get a 0 on the top output, 1 on the second, and if you walk through that, you can see you're going to get a 0, 1. A is fed directly in, so you're going to get a 0 on the third, and they're both fed directly, so you're going to get a 0 on the fourth. And you could continue down and look at the combinations, but you get a 1 on the third AND gate if AB is 1, 0, and you get a 1 on the last bottom AND gate only if A is 1 and B is 1. So this is a decoder. Next up is the multiplexer. We have a 4-to-1 mux. This is a little bit different in that it has a selector signal, S1, S0, and it will pass, in this case the 4-to-1 mux, will pass one of 4 values to the output depending upon the combination of S. If it's 0, 0, 0, 1, 1, 0, or 1, 1, it'll pass respectively A, B, C, or D to the output. This is a full adder, probably the most recognizable combinational logic circuit. And this full adder has, it adds 2 single bits. It produces a 1-bit sum. It handles carry in from the previous bit, and if it's bit 0, carry in is 0, always hardwired as 0, and carry out, which is overflow. So here you see the logic table, the truth table on the right hand side of this. Obviously if A is 0, B is 0, and there's no carry in, S is 0 and there's no carry out. It's not until you get down to A is 0, B is 1, carry in is 0, you get a sum of 1, no carry out. Then when you get to A is 0, B is 1, and you got a carry in, you're going to have a carry out. In other words, 1 and 1 is 0 with an overflow or a carry out of 1. When you have a multiple bit adder, and I think the next slide we look at a 4-bit adder, the carry out of bit 0 is the carry in for bit 1. The carry out for bit 1 is the carry in for bit 2, etc. So this is how you handle binary addition. This is the underlying circuitry necessary to handle the addition of 2 single bits. As you can see, as we start to review larger implementations, larger circuitry, we have to use more abstraction. So in this case, the box labeled full adder is all of the circuitry that we saw on the previous schematic. And you've got, so for bit 0, the carry in is obviously 0 because there's no carry in on bit 0. Can't happen. You've got A sub 0, B sub 0, S sub 0, which is the output, the sum, and you've got your carry out. Your carry out for bit 0, it becomes the carry in for bit 1. Your carry out for bit 1, carry in for bit 2, etc., etc. So for the 16-bit ISA instruction set architecture that we're going to use in this class, you have a 16-bit adder for addition because it's a 16-bit instruction set architecture. So you have this circuitry times 4 to add one 16-bit value to another 16-bit value with full carry in and carry out support. So given what we now know about logic circuits and De Morgan's law, it's safe to say that we can implement any truth table with and, a combination of and, or, and not. So here is a combinational logic circuit similar to one you're going to see in the homework for this particular chapter, this lecture. And there is the truth table. It has 3 inputs, 1 output, and if you trace A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, all of the possible 2 to the n possibilities, so yeah, I got 3 bits input. That with 3 bits, how many combinations can you have? 2 to the n or 8, and that's 0, 0, 0 to 1, 1, 1, which is actually 7. You could trace all of those combination of inputs to a single output, and there's the truth table. This is where we are going to end our discussion of combinational logic circuits, and we will also begin our next lecture discussing sequential logic circuits. But just to review the difference between the two, a combinational logic circuit always gives the same output for a given set of inputs. So for example, an adder always generates a sum and a carry regardless of the previous inputs. It's only based upon the current inputs. Sequential logic circuits, they store information from one state, that's a critical term, from one state to the next. What is the smallest increment of change from one state to the next? In a processor, it's 1 clock cycle. So it's pretty quick, unbelievably quick. The amount of time is billionths of a second, but we'll get to there as we move forward.